Hello everyone, welcome back to the class real time system. Today we are going to discuss about the code sharing. So what is the code sharing? Some action is to be carried out by the several different tasks. Okay, so common practice is to use the subroutine. Okay, it is shared. It may causes the inconsistency in multitasking operating systems. Okay, so for example, we have the two tasks. Okay, so the two tasks need wants to access the subroutine. Yes, so here the subroutine which is specified here is yes. So locally it is held, the data is yes, which will be changed. Okay, so here we will be having the task A and task B. So the task A, these are the line which are represented by the instruction. So these are the instructions which is keep on executing. At the line 4 it calls subroutine. Yes, subroutine. Yes, so the subroutine yes is nothing but on this program. So it is executing the subroutine program. So yes, data for A. Okay, subroutine data for A's program. So it is keep on executing the subroutine program. Once if it is completed, this line will be returned into the next instruction and it is keep on executing the task A. At the same time, when it is executing the subroutine program, the task B is started executing. Okay, task B is started executing. At this point it calls the subroutine. Yes, the same program whatever it is executing here, the same program which will be called by the task B. So the task B which is called the subroutine program, the same time the subroutine program is also called and it is executing. So in this, the thing is there is a possibility of overwriting A's data into the B data value in the B's environment. Okay, so to avoid that, we are going for the code sharing. What is the code sharing? There are two methods are used to solve these kind of problems. One is the serially reusable code and second one is re-entrant code. So what is the serially reusable code? Here the serially reusable code which uses a lock mechanisms. So once the task which is called the subroutine, then it completely the subroutine program is locked. Okay, once it will be unlocked whenever the subroutine program is completed, so that time it will be unlocked. So that time the other task can use the subroutine program. Okay, so the serially reusable code is nothing but some form of lock mechanism which is placed at the beginning of the routine, such that if any task is already using the routine, the calling task will not be allowed entry until the task is using the routine unlock it. Okay, it is also the example for mutual exclusion. And the next is re-entrant code. Re-entrant code is nothing but whatever the subroutine program, it is nothing but a pure code. So there is no data can be stored into that particular area. So whatever the task which is called, so in that particular area the data will be stored. The subroutine data will be stored. Okay. So if the subroutine can be coded such that it does not hold within it any data, that is it is purely coded, any intermediate results are stored in the calling task or in the task is associated with the task, then the subroutine is said to be reentrant. So in this example, the task descriptor for each task which contains a pointer to the data area, usually a task area which is used for storage of all the information which is relevant to that the task when using a subroutine. Hence, a start pointer would be saved with the volatile environment and will be stored when the task which resumes. So it can be shared among the several tasks which contains the no data which is relevant to the task can be stopped or started anytime without loss of information. So the data held in the working register of the CPU is stored in the relevant task descriptor when the task swapping which takes place. So here commonly we can see this the PID. Okay, so in this PID there are loop descriptor 1, 2, 3. So the number of loop descriptors are there which executes the number of tasks. So the each task will be controlled by this PID code. So this is all about your code sharing. So the code sharing is nothing but one code can be shared by multiple tasks. There is a possibility of overwriting one data into the another data. That's why we are going for the code sharing. To avoid these kind, we have two methods. One is re-entrant method and another one is serially reusable code. Okay, so this is what we have discussed in the code sharing. Now the resource control. So one of the resource control we are going to take an example is input output subsystem, IOSS. So what is IOSS? IOSS is nothing but an input output subsystem. So one of the most difficult area of the programming is the transfer of information to an external device. So the availability of the well designed and implemented input output subsystem is essential for the efficient programming. Okay, so this enables the application programmer to perform the input output by means of the system call, either the high level language or from the assembler. So the input output subsystem, which handles all the details of the devices, also it deals with the problem of several tasks attempting to the access of the same device. So the typical input output system is divided into two levels. The two levels are the input output manager, which accepts the system call from the user task and transfer the information which is contained in the call to the device control block for the particular device. So whatever the information which is supplied in the call by the user task will be example for the locations of the buffer area in which the data to be transferred, it is nothing but an output where it is exactly it is stored, or to be stored, that is nothing but an input, the amount of data, types of the data, either it may be an ASCII data or binary data, and directions of transfer. Okay, so the actual transfer of the data is between the user task and the device that will be carried out by the device driver by using the informations in the DCB. Okay, so the input output manager will receive the commands from the user, and that will be sent to the DCB, device control block. So the separate device driver may be provided for each and every device access, or a single driver may be shared, shown in the figure. The next line, there will be a DCB or the different DCB, I mean device driver, which will be mentioned in this diagram. So what is there in the DCB? So the DCB block is nothing but a device control block. The device control block which contains the information which is related to the device. So what is the physical device name, the type of the device, and device address, interrupt address, and interrupt service routine address, and then device status. Okay, similarly, the data area address, and then bytes to be transferred, then current byte account, and then if it is on binary data transfer or ASCII data transfer, so these all the informations will be there in this device control block. So this is the diagram which represents the multiple driver that can be accessed to each and every device. For each device there will be a separate device control block, device driver. So in this next diagram you can see this, the user tags that will be sent to the input output manager. From this input output manager it is sent to the DCP, device control block. From the device control block there is a single driver. That single driver will manage all the information, will connect all the devices to the single driver by using that interrupt service routine, and also a interrupt service routine. By using that, the device will be selected and that will be accessed. That particular device will be accessed by the user. So this is what the diagram which represents. And in a multitasking system, there is a provision has to be made to deal with the overlapping request for the particular devices. For example, there are several tasks that may wish to send the informations to the log devices. So normally the way of handling this is a single user environment is to send a record, that is one line at a time. A return is being made to the user program between each lines. Okay. So this is done in a multi-programming system. If the printer is not allowed to the specific program, then the output from the different programs can become a intermingled. So this solution usually used is to spool the output, that is intercepted by the operating system and stored in the file on the disk. When the program terminates, the content of the spool file associated with that, the programs used in the printed output. So the similar approach can be used in the multitasking environment, which is provided that the user task can force the printout of the spool file of the task. So there is still the problem what action to take if the device is in use when the user task make a request to use it. The several possible solution which include suspending the task until the device becomes available, and return immediately to the task with the information that the device is busy, and leave it to the task to decide what action to take, normally to call a delay or try again later. So add the request to the device request queue and return the calling task. So the calling task must check at the time to see if the request has been completed or not. A good OS will provide a programmer with a choice of actions. So the option 1, which is referred to as non-buffered request, in that the user task and the device have to meet can thought as the equivalent of the hardware handshaking. So option 2 is nothing but an equivalent of pooling and rarely which is used. Okay, one of the option which is 3, which is represented here, is buffered request. Is in the form of message passing. The user task passes to the input-output subsystems the equivalent of a letter with a message and instructions about the destination, and then the user task which continues to the assumption that eventually the message will be delivered. Usually, some mechanism is provided which enables the user task to check if the message has been received. That is some form of recorded delivery in the input-output subsystem records the message has to be delivered to allow the user task to check. So the buffered input is slightly different in that the user task invites the external device to send it in message. This can be considered as an equivalent of providing your address to the person or a group. So the input-output subsystem will collect the messages and deliver it, but it is up to the user task to check its mailbox to see if the message has been delivered or not. So this is all about your code sharing and also input output subsystem. I hope this video is very helpful for you. We'll meet you in the next video. Thank you all.